All right, everybody, Math 3A. This is time for examples for 4.2. Sorry this is going up so late, but I had to do a lot of remembering and some improvising in terms of how I can get these problems back into the groove of working these from home. So let's get to it. Yeah, just as I start, the dogs are going to start barking. Wonderful. So here's what I'm going to work on. Let me just show you my plan. Here is the questions I'm going to work on for 4.2, and I will put this in the YouTube, okay, and I'll actually send it as well. But 4.2, these are the examples I'm going to do for 4.3. Here's the 4.4. All the problems I'm going to do as examples for 4.4. And even though I haven't actually lectured on 4.5, after I do, though, you'll have these already loaded. And it's basically plugging stuff into formulas. So you could even try it on your own, but we will do this. I will load this one as well. I am going to cover the questions 1 through 12 as part of the lecture. So quick summary of what we've already talked about. Over here, you got to be able to convert from logarithmic form into exponential form, backwards, forwards. Base to the across equals what's inside. Log base b of x equals y means base b to the across y equals what's inside that x. Base to the across, that's how you convert it. Base to the across equals what's inside. Base to the across equals what's inside. Properties. No matter what base we're taking, log base b of 1 is always 0. You take a log of a 1, you get a 0. Log base b of itself. If the base is 5 and you take log base b of 5, just 5, it's a 1. Any logarithm of itself, base whatever of itself, is a 1. I should separate these two. So you kind of hard to see that's 3 and 4. 3 has 2 parts. They're inverse functions. They undo each other. Log base b of b to the x. Since the logarithm is base b, and inside you have an exponential function base b, because the bases are the same, log base b undoes b to the x, and out pops the x. It undoes what happened to that exponential form. Likewise, b to the power. So the base of the exponent is b, raised to a logarithm base b. Because the bases are the same, they're going to undo each other. Out pops that x. And when we get to the solving of equations, one of the properties that's going to help us, if you have a logarithm equal to a logarithm and the bases are the same, log base b of an x equals log base b of a y, then inside has to be the same. X has to equal the y. Now, we'll talk about those other things as we continue into 4.3 and 4.4. But for right now, number 11, just looking at the homework so you can see exactly what I'm talking about. So 7, 9, 11, 13. On number 11, what they want for you to do is to take this logarithm form and write it in exponential form. So change it to an exponent. And then when I do number 17, they're giving you the exponent form and they want you to write it, convert it into log form. That's all. So it's all about base to the across equals what's inside. You're not solving anything because there is no x. You're just rewriting it. So base 32 to the across, which is a 2/5, equals what's inside 4. That's all you have to do. Stop right there. Change the log form into an exponential form. And over here, I don't have a fancy mantra for converting exponents into log form, for going backwards. Technically, there is no forwards or backwards. It's just base to the cross equals what's inside. So here's what I hope you realize. When you're supposed to convert this into a logarithm, It is a logarithm base, something goes here, of something on the inside equal to something over here. Log base something of something equals something. Because how do we do this? Base to the across equals what's inside. That's what we did to convert it to this. So now you just got to play, where is everybody? Because I got to fill in these empty boxes. Somebody went base to the across, base to the across. The base over here is 81. The bases are the same. So somebody did base to the across and got 81 to the 1/4. So the base that goes in here is the 81 to the across to the power. This is where the 1/4 goes. Base to the across equals what's inside. So the equals what's inside, that's what goes in your logarithm. So your final answer just looks like log base 81 of 3 equals 1/4. That's what you do. Now, as I write up the next set of problems, I'm going to pause in between. So on 28, they have f of x is log base 10 of x, and they want you to evaluate on your calculator, plug in 4/5. They want what is f of 4/5. So that means what is log base 10 of 4/5. So nothing fancy, you're just plugging it into the calculator. And 4/5 is one of the things our calculator does. So right here, log base 10, this is the log base 10 button I showed you in class. Plug in 4 divided by 5. Make sure you close the parentheses. And it's negative 0.0969100013. The directions say round to 3 decimal places. Let me double check. They do round to 3 decimal places. I looked in the back. So make sure you just round to 3 decimal places. So that would be negative 0.097. Okay. Number 32 and 34. Again, with the directions. 32 and 34. The directions say solve for x. Solve for x. So you guys are doing the odds, of course. I'm going to do 32 and 34 as an example. Use the properties, use the definition as needed. 32, you have log base 5 of x. Over here, you have log base 5 of 5. Over here, you have log base 5 of x. We want to know what x equals. Well, since it's log base 5, that's the fourth property down here. If the logs are the same, if the bases are the same, then this inside has to equal that inside over there. The 5 has to equal the x. That's done. Number 34. Property number 3. This is a log base 3, and inside you have an exponent base 3. Because the bases are the same, log base 3 undoes 3 to the negative 5. Log base b of b to the x is just this power on this side, negative 5. So negative 5 equals that x. That's all you do. Know your properties. Know your properties. Okay. It's quicker that way. Now, if you forget, I mean, you do get to, it's an open note test, you technically, because it's a take home, but on the final, it's still open note. If you didn't remember, base to the across, 3 to the x, equals what's inside, which is 3 to the negative 5. So that x is still that negative 5. They have to be equal. Right. Next set. Okay, so for number 38 and 40, use the properties of logarithms to simplify the expression. So you're doing 37, 39, take a look at 38 and 40. 6 to a logarithm base 6. That's a 6, a logarithm's base 6. So you have an exponent base 6 to a log base 6. It's the property number 3 down here. If the base of the exponent is the same as the exponent, the logarithm that you're raising it to, they undo each other. So the answer is just 36 times x. That's all that pops out. It undoes that log base 6 up there. Now, 40 is a little trickier because of the 1/4 that is out in front. You don't know these other 3 properties over here yet. Now, later on, we could do the problem either way, but let's just do it this way without those properties. 1/4 times, you're supposed to use these properties of logarithms. So this is 1/4 times the log base 4. 16 is 4 squared on the inside. That 16 can be written as a base 4, 4 to the 2nd power. So in that logarithm, you now have a base 4 of an exponent base 4. Since the bases are the same, this is now just 1/4 times log base 4 of 4 to the 2nd is 2. It's 1/4 times 2. Let me clean that up. 1/4 times 2. And 1/4 times 2 is 2/4, and 2/4 is 1/2. This equals 1/2. Okay. Now the next one's a graphing problem, so I'm going to get that set up. So for number 42, again, I'm not going to make you graph, but that doesn't mean you might not see, again, I'm talking again, but saying the same thing over and over again. You may see a graph as a bonus question. You may see it as a multiple choice test question. You never know. Multiple choice can be, so you don't have to graph it by hand. But you have to understand, if you're going to graph logarithms and exponential functions, remember the rule. They're inverse functions of each other. They undo each other. Yeah, that's part of it. But inverse functions is basically trading domains and ranges. So switching X's and Y's. The directions explain this perfectly. Sketch the graph of the F function, 5 to the X, and then use that to sketch your graph for the G function. Because it's really difficult to plug numbers into a logarithm function because they don't come out as nice answers. It's hard to pick simple numbers to plug in, but 5 to the X will give you simple numbers out. So here's how it works. We're going to graph 5 to the X first, and it's going to be the same thing no matter what. Remember, an exponential function is always going to do this. That's not showing up so well. Green is just not cutting it. Let me see if this green's any better. That's a little bit better. You see, that's a little bit better. Start with 0. 5 to the 0 is 1. 5 to the 0 is 1. We always know that it's going to go right through here. Unless there's some kind of vertical shift or horizontal shift, it's going to go through the Y. It's going to have a Y-intercept of 1. 5 to the first, when you plug in 1, you're going to get a 5. When you plug in 1, we get a 5. When you plug in 2, we're way up there at 25. 5 to the second is 25. When you plug in -1, 5 to the -1 it flips. It's 1/5. So it's really small. When -1 goes in, we get 1/5. The exponential functions, if the base is bigger than 1, if that's a positive X, it's going to always look like this, and it's always going to increase really quickly. So the logarithm, we switch these ordered pairs. On the logarithm function, instead of -1, +1/5, you're going to have 1/5, which is real, about right here, and then -1 is the y. 1/5 is your x, -1 is the y. You switch the order pairs right about there. If this is 0, 1, then 1, 0 is going to be on the logarithm, the inverse function. If 1, 5 is on 5 to the x, then on the logarithm, it's going to be 5, 1. Switch the order pair. And then way down there, if this is 225, then way down there, you're going to have 25, 2. And so it's going to go like this. That's what your inverse functions look like. Here is your g of x equals log base 5 of x. And over here is f of x equals 5 to the x. Okay. Okay. With 46, again, you got to do some graphing by hand, but that's not as important as the actual questions you have to answer. So the questions I'm talking about are these guys. They want you to find the domain, the vertical asymptote, and the x-intercept of the log function, and then sketch it by hand. But I'm more interested in making sure you understand domain and vertical asymptote and x-intercept. So, domain, log base 10 of x minus 1. Now, according to the definition of a logarithm, y equals log base b of x, we have some rules. The base has to be positive and it cannot equal 1. The base has to be greater than 0 and the base cannot be a 1. You can't take a log base 1 and you can't have log base 0 and you cannot take a log base of a negative. Also, inside of the logarithm, you can't plug in 0, you can't take the log of a 0, and you can't take the log of negative numbers. So the domain of just any logarithm, if it's just a plain old x with nothing special done to it, that x would have to be greater than 0. They have to be positive numbers if it's just a regular logarithm. So here, for this function, this x minus 1 that I'm trying to plug into log base 10, that x minus 1 has to be greater than 0. So that means, add 1, the domain of this function, any x that I choose to plug in, has got to be bigger than a 1. If I plug in 0, I'm taking the log of -1. I can't do that. If I try to plug in 1/2, 1/2 minus 1 is -1/2. I can't take the log of a -1/2. I can't even plug 1 into this. Log base 10 of 1 minus 1 is the log of 0. I can't do that. I have to plug in numbers. I'm only allowed to use numbers that are greater than 1. So the domain, all your x's are greater than 1. And I don't know in the back if they just leave it like this or if they use interval notation. The interval notation would be greater than 1, parentheses 1 to infinity, if they use interval notation. They've been switching back and forth, so that's why I'm putting that there. Now, vertical asymptote. Here's what that's talking about. If we just graph simple y equals log base 10 of an x with nothing special, then we know it's the inverse of 10 to the x. It's going to do this, just like all the other logarithms do. And it's going to go through 1, 0, okay, of this. And the vertical asymptote on a simple normal logarithm base 10. On this one, this vertical asymptote is x equals 0, the y-axis. It's not going to cross the y-axis. Supposed to be an arrow. The vertical asymptote is x equals 0. So if you take y equals log base 10 of x minus 1. Remember what we did back in chapter 1. If you mess with x, you're moving the graph left and right. It's a horizontal shift. And because it's in the parentheses with x, that's a built-in negative every single time. So the negative is built in, which means you're going to shift it the opposite sign, the opposite, x minus h. So the horizontal shift is a positive 1 to the right. And when you think about it, look at the domain. The domain used to be greater than 0. Now it's bigger than 1. It's got to be here is your vertical asymptote at x equals 1. Not to mention the x-intercept. On just simple y equals log base 10 of good old plain old x, the x-intercept is 1, 0. But if you do x minus 1, it's going to shift 1 unit to the right. So if you're at 1 and you go 1 to the right, that's now going to be here at 2. And that's going to be your x-intercept at x equals 2. Oh, look, I already graphed it. That's all they're asking for. So on 57, all they want is describe the transformation. You're starting off with f of x equals log base 2 of x. So what's the transformation if we do g of x equals 4 minus log base 2 of x? Okay, so here's the rule. If you change the sign of the function, that's a reflection across the y-axis, sorry, the x-axis. It flips it vertically. So you have a positive log base 2 of x here, and this is now a negative log base 2 of x. So that's going to be a vertical transfer, or a vertical flip, or sorry, it's going to be it's going to flip across the x-axis. And I know I'm not wording that correctly, so I apologize, which means I can just pause. And while I pause, I can think about it. The word I was looking for is reflection. A vertical reflection across the x-axis. So when you change it to a negative, it's going to reflect across the x-axis. Now, if you have inside an x minus an h, that's a horizontal shift, okay? The negative is built in, so if you see x minus 2, that's a positive 2 to the right. If you see x plus 3, then it's a negative 3 going left. And then if you change something after the function, a k value, that's a vertical shift up and down. So the problem with this is that it's written usually in the wrong order. So you have to realize that this is a positive 4, negative log base 2 of x. And then you have this technically a plus 4. That's the k. Look at why it's written like this, though. When it's written like this, students will get this confused and think that inside the logarithm is x plus 4. You're actually supposed to go x plus 4 and take the log of it, but there's no parentheses. That's why parentheses, whether they're there or not, are important. So the safer way to write it is to put 4 minus that, and that way you know the 4 is not inside the logarithm. So these are the same things. This is a k value of 4. So it's a reflection across the x-axis, and then it's a vertical shift up 4. Okay, our next set of problems, 62 and 66. Look at the directions. And it says, write the logarithmic equation, change the logarithm into exponent form. So we're going to do exponent form again. But this time we're doing natural logarithms because we have base e's, natural logarithms. Okay, natural logarithms. So here we go. Number 62. The natural log of 4 is equal to 1.3862, and it goes on forever. You need to remember when you see ln, and I always write it with a capital L, that's just me. Natural logarithm of 4 means there is a base down here. We don't write it, but that's a base e down below. It's just base to the across equals what's inside. That's all they want from you. Base is e to the across 1.3862 equals what's inside 4. Now I'm going to tell you something that's wrong. Look at the directions one more time. The directions give us an example of what they expect. Natural log of 5 is 1.6094 and ... And when they convert it, if you want your answer, your conversion to actually be true, when you convert it, you need e to the 1.6094 with the ... If you don't put the ... you ain't going to get exactly 5 on the other side. It's not going to happen. So you have to have the ... Okay. So that would be marked wrong. It's going to be, don't forget because that's what it is right here. They're not rounding. They just want you to rewrite this in its log form. If I punch in e to just the 1.3862 without the dots, and by the way, no, you don't have a button on the calculator that gives you the dots. But if I just punch it in and stop at 1.3862, I won't get 4. I'll get something close to 4, but I won't get 4. So when you're just converting it, when you're just rewriting it, just put everything they give you. 66. Convert. Natural logarithm has a base of e. That's not the base. This is the inside. 1 over e squared is what's inside my natural logarithm. But down here, that's not written. Base is e to the across, -2, e to the -2 equals my inside, which is 1 over e squared. And that needs to make complete and total sense because, sorry, not 1 over e squared, no negative. That makes sense because if you have a negative power, that means reciprocal. It's going to be 1 over e to a +2. That's the translation. So you got to get used to seeing or remembering there's a base e down here when you do the conversion. Now the directions for 72. We're starting with the exponent form. Whoops, hold on. We're starting with the exponent form, and they want us to convert it into the logarithm form. And since our bases are e's, we're going to be converting it into natural logarithm form. Okay, natural logarithm form. Okay, so remember, it's all about somebody undid my natural logarithm. Somebody took my natural log of something equals something over here because they did that base, which is an e to the across equals what's inside, and came up with this. So the base is e, there's the base, which you wouldn't write because natural log takes care of it. E to the across, the 2.5 goes across. E to the across, e to the 2.5 equals what's inside. That's where the 12.1824, don't forget the dots. So that's, if I was going to try to figure this out and have something, and not necessarily I have to have something to show, but to kind of put my brain in the right perspective of where everything goes, I might draw some boxes and fill them in. And then my final answer, clean it up. The natural log of 12.1824 ... is 2.5. Same thing over here. base to the across equals what's inside. Somebody took the natural log of something and they got something. Now, that's not E. That's 1 over E to the fourth. Over here, that's E to a positive 2.5. That's not E to something yet. You need to rewrite this in order to convert it because it doesn't work if it's in the denominator. You need to see that 1 over E to the fourth is E to the negative 4 equals 0.0183 dot, dot, dot. This is E to the negative 4. So now base to the across equals what's inside. The base is E, E to the across, that's where negative 4 goes, equals, this is my inside, 0.0183. So the natural log of 0.0183 dot, dot, dot equals negative 4. Okay. Number 80. You're given this function, f of x equals 3 times the natural log of x, and they want you to evaluate what does it equal if you plug in square root 0.65 into that natural logarithm. That's all. So make sure you're plugging it into the correct button. So real quick, I'm going to make sure I want to write it out. So that means f of square root of 0.65. So I'm going to get 3 times the natural log of, inside my logarithm, the square root of 0.65. Order of operations, okay, you can actually just punch this in exactly as is. Let's just punch it in exactly like that. I'll show you. So I want the natural, or 3 times, here's my natural logarithm. And then inside, I'm taking the square root. Oops, not the square, back up. The square root of 0.65. Close the parentheses that's in the square root, and then close the parentheses that's for the logarithm. So 3 times that is negative 0.64617,43741. The directions say 3 decimal places. I'm in the screen share, so it's not going to see what I'm doing. So 3 decimal places, negative 0.646. Making sure you can use your calculator correctly. Now, 82, 84, 86, and 88, no calculator. You should be able to do these without a calculator. They're just the properties of exponents. 82. Negative natural log of an e. Negative 1 basically times the natural log of e. The natural log is base e. Inside, you have an e. This is the second property. If you take log base b of b itself, if the base of the logarithm is what you're taking on the inside, it's a 1. So the natural log of an e That's 1 because the base of the natural log is 1. Sorry, the base of the natural log is e, and you're taking the natural log of inside as an e. This is negative times 1, which is negative 1. The natural log of e is 1. You have to remember, we don't put the base. When you just see natural log, there is an e down here. We don't write it. So this e that is written is what's inside. It's the inside of the logarithm. So the natural log of e means, since that's an e and that's an e, they undo each other, we get a 1. This is that first property. Whoops, my bad. Where am I looking? Now, technically, it is the first property. You know what? It's a combination. It's a combination of property 3. You can think of it as property 1. There's a lot of ways to look at this. Property 3, log base b of b to the x. If the bases are the same, then log base b undoes b to the x, and you just get x. So whatever that is, that's the whole thing. Natural log is base e. Inside you have e to the 0, which is base e. So the natural log is going to undo that e exponent. This whole thing is 0. And 7 times 0 is 0. And I know I was probably speaking too quickly. 7 natural log of e to the 0. Everything to the 0 power is always 1. So this right here, that's a 1. So this would be 7 times the natural log of a 1. And then if you take the log of 1, it's a 0. This is 7 times 0. So you get 0 either way. That's 84. On 86, it's the other version of property number 3. 86, when you have the base of your exponent being raised to a logarithm base b. Base of the exponent, base of the logarithm are the same thing. Of an x, they undo each other, you just get the x. So since this base of the exponent is e, raised to a logarithm base e, they're going to undo each other and you get 22. That's all. 88, the natural log of 1 over e to the 4th. Here's what I hope you see. That's a natural log, it's a base e. Hey, that's got an e in it as well. It looks a lot like property 3, which we've done already. It looks a lot like it might be log base b of b to the x. The problem is, it's not e to a power, it's 1 over e to a power. Rewrite it. This is exactly the same as the natural log. Instead of 1 over e to a positive 4, you can change this to e to a negative 4. 1 over e to a positive is the same as e to the negative 4. So now the base here is e. Inside you have a base e. So they undo each other and you just get negative 4. All right. So that takes us through 86, pulling up 88. That was 88. Pulling up the next one. Okay, number 109. It's one of those frightening word problems. So don't let it frighten you. Hang on a second. There we go. Okay. So. Psychology. Students in a math class were given an exam and then tested monthly with an equivalent exam. The average scores for the class are given by the human memory model. Okay, that's a psychology term. The human memory model on time, based on time, is 80 minus 17 log base 10 of t plus 1 for the interval from 0 to 12. Basically, t in between 0 and 12, where t is in months. So for a year, 0 months to 12 months, that's a year. First question, what is the average score on the original exam? In other words, let t equal 0. So this is something you should be able to do without using a calculator for this one problem. If I just plug in 0, f of 0 would look like 80 minus 17 log base 10 of 0 plus 1. So that f of 0 is equal to 80 minus 17 log base 10. 0 plus 1 is 1. And then f of 0 is equal to 80 minus 17 log base 10 of 1. Anytime you take the log of 1, it's always 0. That's 17 times 0. So for 0 months, for the initial test, it's 80 minus 0. The initial average on the test is an 80. That's the initial average. They give you everything you need. You just need to understand what you're supposed to do with it. So take it slow. It's not going to be overwhelming. But for the rest of them, I showed you the other day how to use a table instead of having to now, because for part C, they want you to plug in for 2 months, and for part C, for part B, 2 months. For part C, they want you to plug in 11 for 11 months. So if you just go to a calculator, and if we type in the equation into your y equals, and I already did that. So I have y equals, let me move this over here so I can see. I have 80 minus 17 log, and that's my log base 10 of x plus 1, because my calculator only will think in terms of x's when I'm in this mode. You can't plug in a t. So there's the equation. And then I just go to the table. And the first number I plugged in was 0. When I plug in 0, the answer better be 80. Yep, average is 80. And then if I plug in 2 months, t equals 2. So instead of doing it by hand, the answer is the average score is a 71.888938, and then round to the nearest 10th or 100th, whatever they want you to round to. And then for 11 months, now you let x equal 11. Enter. And the average is going down because it's basically the same test, and they're trying to test, do you remember after 11 months, what's the average score after 11 months based on your memory alone of what you've been taking a test on all semester long? And the average would be 61.65. All right. So those are the homework examples for 4.2. I have a meeting that's going to start up in just a few minutes. So I'm going to post these. And after my meeting, I will record 4.3, 4.4, 4.5. And I also got to record my trigs. So I'll be here all night long. I'll be here all week. Tip your weight. Never mind. You wouldn't laugh anyway. So stay tuned.